All right, let's get started. So, everybody settle down, settle down. All right, so you all have a homework assignment due today. I'm just going to have you all turn that in here if you haven't already done so. Now, you have homework 3 has been assigned today. It is not due until, that was pretty good. It is not due until February 18th, but our first celebration of learning is going to cover homeworks 1, 2, and 3. So this is it. We're actually approaching the end of what will be on Exam 1. In fact, Exam 1 will cover everything up until today. It'll cover block shear rupture, and then it'll cover our final topic in tension members, which is threaded rods. Did I mess something up? You're exactly right. It is, all right, so I made a mistake. It is due on the 18th. And so what I am wrong on is that it is Monday. So there was no box around it, though, so it's only, that's a dashed line. It's not a box. I don't know what you're talking about. Okay, so thank you. It is Monday. It's the 18th. It is the 18th. Hold on. Shh, can't hear him. Yes. The test. Oh, that's a good question. I think it's the 20th. Let's see. Yep, it's the 20th. So we are going to have our exam review Monday and our test on Wednesday. I'm glad you said that. And here's another thing. I don't know how it happened, but we're on schedule. It's because we're talking about block shear today. So I don't know how that happened, because with me having the flu and whatnot. But, hey, what that means is as long as we stay on schedule that day before spring break, it'll be a makeup day. So as long as we're on schedule, we won't meet that Friday. Unless you really want to, we can talk about composite beam design and all sorts of stuff. I'm not seeing very much excitement meeting the day before spring break. I thought y'all liked me, but okay. Yeah. All right, so sound good? So today, what we're going to do is we're going to have a full-blown example on block shear. We're going to, if we have time, we're going to talk about the Kansas City collapse, and then maybe we'll introduce the concept of threaded rods. But we'll see where we're at. Let's sort of recap block shear. If it'll load. Okay. So remember, block shear is kind of unique. It's kind of weird in terms of how it happens. In terms of identifying the block shear failure path, really there's a few key rules that you got to follow. Number one, there has to actually be a path of the steel that's in shear, and I'll show you what I mean by that here in a second. It has to fail in such a fashion that it keeps all of the bolts intact. And third, there's a little bit of a common sense approach you have to apply, and that'll become clear after we look into our example. Now remember, here's our expression for block shear capacity. I know, it's a little weird. You have a pile of junk less than or equal to a pile of junk. There's a bunch of areas in there, some AGVs, ANTs, all this stuff. Don't worry, I think after the example today, you'll find it's actually pretty straightforward. Our phi value for block shear is 0.75. And so other than yielding and tensile stresses, you pretty much have all the skills that you need to compute block shear capacity. It's just going to be a unique cross-section, if you will. Remember, when you I mentioned this last time, whenever you have a spec equation that says a pile of junk less than or equal to another pile of junk, that's basically the spec's way of saying it's the minimum of those two quantities. So I've got those two quantities. what I can do is I can simplify those a bit by factoring out everything that's common. And so I get the expression that's in the box. And so basically that's the tensile capacity plus 0.6 times the minimum of these two shear capacities. And remember the 0.6, that comes from the von Mises yield criterion. So the idea that you know, in normal stresses, it yields when the stress hits Fy. But under shear stresses, it yields when the stress is about 0.577 Fy. And so the folks who wrote the spec said, just call it 0.6. Close enough for government work. Yes, sir?
So what is the reason to go, 0.577?
That's a good question. It's really just the decision of the folks who write the spec. If you open up the bridge spec uses 0.58. So that's just their choice. It's just close enough. Keep it simple. When we start looking at bolt bearing and bolt ovalization and bolt tear out calcs, if you look at the bolt tear out equation, you'll see a 1.2. And the 1.2 comes from 2.6 values. So just to keep everything simple. So I agree that from a mechanics standpoint, you just using 1 over the square root of 3 would actually be a little bit more exact, but you know, we're not splitting atoms. I mean, it is steel design, so there's a little bit of room for keeping it simple. So, and I'm not saying that to be facetious or be a smart. I mean, I'm being serious. A lot of times in the spec, you'll see instances where, you know, here's the theory, and let's just go with this. So, any questions? All right. UBS is always going to be 1 for our purposes. I just wanted to include the one case where it isn't, but it's going to be 1 for us. This is what I was talking about earlier when it comes to defining a block shear path. You have to define a failure path that keeps all of the bolts intact. So imagine if this brown plate separated from this green plate, the bolts wouldn't shear. They would all remain intact. If this brown plate separated from this green plate over here, all of the bolts would remain intact. You wouldn't be shearing through them. The one other thing that I would mention is that your block shear path has to include a path of shear, because, you know, here's a potential block shear path. Here's a potential block shear path. I suppose another one is this, but what about this? Well, that's just net section fracture. There's no shear, right? So there's no reason to evaluate it because you've already evaluated it when you do net section fracture. So it has to actually include some component of shear. Does that make sense? Okay. So what we're going to do is we're going to do this example together. I'm going to help you identify the failure paths and whatnot, and we'll do all the math together. Now, just so everybody is aware, this is the one we did in example 4. It's the exact same problem, okay? It's a 40-foot long, W8 by 24, A992 steel, 3/4 inch diameter bolts. This is the exact same problem that we did in example 4. So remind me when we do this, I'm going to pull up the sheet, but I want you to give me some values because I want to be able to make a comparison to what we did before, just to see how everything shakes out. Because remember, there are 3 limit states for tension members that we need to verify. We have gross section yielding, net section fracture, and block shear rupture. Up until now, we've only been considering 2 of them. So for all we know, we compute the block shear capacity, and it might govern. It might not. We'll see. So let's just sort of see how this shakes out. All right. Give me a sec. There we go. Now, help me out with a couple things. What was the gross section yielding capacity of this member? Remember, this is example 4. So what did we get for that? 318.6. What about net section fracture? 255.6. Right? Okay. So if the block shear capacity for this problem came out to be like 205, then it would govern, right? That would actually be the capacity. In other words, it would endure block shear before it yields or fractures, okay? We just have to go through this calculation and see. Before I continue, there's actually one other value that I'm going to need, and that's the flange thickness. What was the flange thickness for a W8 by 24? 0.400, right? Okay. Sound good? All right. Now, I'm going to help you identify the failure paths for this, and I'm going to do it a little bit of a unique way. Okay. I want to draw this section out a little bit three-dimensionally, so please forgive my art skills. Okay, so here's the section, and I'm only looking at the top. Okay, now for this sort of determination, I'm going to assume that the only bolts I have are one line along one flange. In other words, all I've got is this, and that's it. Okay? That's all I've got. Now that's not really what, I know that there's 4 of these. There's one here, and then there's one on each flange. But I want to see if I can help or use this to help identify what are the potential failure paths. Okay? So one of the rules of defining a block shear failure path is that it has to include a path in shear. Okay? So I propose that my block shear failure path at the very least is going to go through those bolts like this. Okay? Now, as for the path in tension, okay, so there's going to be a path in tension. Let me ask you a question. What do you think is more likely? That I rip through this little bit right here, or I rip through the entire wide flange on the other end? The little piece, right? That's going to be the easiest. So I propose that the failure block, if you will, that rips out of this flange is that, right? Now that's assuming that all I have is one row of bolts, but that's not the case. I've got multiple rows of bolts, or multiple lines of bolts, because I got a similar one over here. So what happens there? Well, I have another similar failure path. Goes down and like that. And then there's a similar one on the bottom, or similar set of failure blocks on the bottom flange. Sound good? Okay. So here's how I'm going to do this. What I'm going to do is I'm going to compute the failure capacity of one of those blocks. And then what I'm going to do is I'm going to multiply that by 4 to get the capacity of all the blocks. Make sense? All right. So what I want to do is I want to look at this sort of in plan view, as if I'm in the helicopter looking down. So let's sort of, sort of look at it like that. That's the best eyeball you're going to get out of me. So from the top, helicopter looking down. Okay, so I propose that looking at this, looking down, here's what I'm going to see, okay? And I'm making it a point to draw this in a particular fashion. All right, so I'm going to see a flange like this. Now, one other thing I'm going to draw is this. What is that? That's the web showing through, right? So if I'm looking up top, there's the flange, but then there's that web, as if that web was right there, okay? So I'm doing that so you can kind of have an orientation of how I'm looking at this. All right? Then, and I'm going to draw the same set of bolts on both ends, but I'm only going to focus on one of them. I've got 1, 2, 3, 4. 1, 2, 3, 4. Right? Okay. Now, remember, I am yanking on this in this fashion. That's the way I'm yanking on it, right? Okay. Now, the failure block that I'm going to focus on, I'm just going to focus on this one over here on the right. It's going to go like that. So this is what I'm focusing on. So let me scroll up a little bit. There we go. Let's get some dimensions on this. Okay? So help me out. What is this dimension right here? 1.5 inches. What is this dimension? That's 2. And then that, and that, they are all what? Sound good? Now, the only other thing that I want to make sure everybody's clear on is this. This path, this little path up here, is it experiencing shear or is it experiencing tension? Tension. This path here, what is it experiencing? Shear. Okay. So I'm going to indicate that on my block. Okay? So I'm going to say that this is the tensile path, and we'll say that this is the shear path. And so I want everybody to be able to recognize that accordingly. Everybody good? Okay. So, remember, we are going to be computing the capacity for a single block. Okay? So, for a single block. All right. So we need gross areas, we need net areas. So let's start off with gross areas. Gross area in shear. I can do better than that. Don't bug me. How do we compute the gross area in shear? Say it again. Exactly right. It's however long this is times however thick it is in and out of the screen, right? Because really what we're talking about, if we look over here at my little three-dimensional, we're talking about that area right there. Does that kind of make sense? Is that getting a little messy? Sorry. So I propose that's 11 inches times the flange thickness, which was 0.4. And so that comes out to be what? 4.4. Square inches. So how about AGT? What's AGT? The gross area in tension. So what's that? There you go, 1.5 times the thickness. I can do that one in my head. Point 0.6. Now, let's look at net areas. Let's do the net area in shear first. in general, how do you compute a net area? You take the gross area and you do what? You subtract the area loss due to bolt holes. Now here's a $64,000 question. How many bolt holes do we subtract for the gross area in shear to get the net area in shear? That's the answer, 3.5. 1, 2, 3.5. We don't go all the way through the hole. We only go halfway through. All right? Does everybody see that? So 1, 2, 3.5. So we take the gross area in shear minus 3.5. That's supposed to be a V. The net area in shear. So, see if everybody's paying attention. How many holes would I subtract for the net area in tension? A half a hole, right? Does that make sense? So this one's going to be 4.4 square inches minus 3.5. What was our bolt diameter on this problem? 3/4. So what's the hole diameter? 7/8. And so what's our net area in shear? We'll say like 3 decimal places. We don't need to get any more crazy than that. 3.175. I have a second on that? All right. And so our net area in tension is our gross area in tension minus 0.5. And so what does that come out to be? Say it again. 425. Do I have a second on that? I heard it. And then don't forget, our UBS is 1.0. Everybody okay with this? So if you're okay with this, all right, here's how we'll go about this. So block shear, getting ahead of myself. Okay, block shear capacity. And what I'm going to do is this. I'm going to write, the first thing we're going to compute is Rn for one block. Because remember, all these gross areas and net areas are all referencing a single one of those failure blocks. But there's 4 of them along the entire wide flange. So what we're going to have is we're going to compute this, then we're going to need to multiply it by 4. So, yes? That's a good question. All right, so UBS is just a block shear reduction coefficient. It's kind of like shear lag for block shear, but 999 times out of 1,000, it's always going to be 1. This is the only instance where it wouldn't be 1. So if you were evaluating block shear of this failure path right here, you would take UBS to be 0.5. And this is only, so what we have here is what's called a coped beam. And so, here, let me, I don't want to hook up my keyboard, so I'm going to, let's see if I can use this. Oh, God. Okay, and so this would be an idea of a coped beam. The idea is you want beam A to frame into beam B so that the floor is flat. So what you would do is, for this little beam that's framing in, what you do is you cut a little bit out of it so that it sits flat. And so if you ever had an instance where you had multiple rows of bolts and you were checking the block shear, that's when UBS would be 0.5. Otherwise, it's always 0.1. So we only in that instance would you ever have to consider it. So that's a good question. Everybody good? All right. So here's our equation. So it's a long one, but it's pretty plug and chug. So we have UBS, FU, and we have the net area and tension plus 0.6 times the minimum of Fy times the gross area in shear, or Fu times the net area in shear. Now, notice how there is, so look, we have a gross area in shear, a net area in shear, there's a net area in tension, there is no gross area in tension. And so you might go, well, Dr. Mike, why the heck did you make us compute the gross area in tension? Well, to get the net area in tension, you need the gross area in tension. So you might as well compute it all. And so let's plug and chug. What is Fy and Fu's? Everybody remember that? 50 and 65, because it's the same thing as before. So and A and T, which one was that? Was that the 0.425? Okay, and then that one, that's the 4.4. This one is the 3, is it 3 point, what was it? 3.175. Okay, this is what I want you to do. Help me out. Okay, first thing I want you to compute is that. What is this? All right, 27.6. So I have a second on that? What are the units? Kips. There we go. Okay, so this equals 27.6 kips plus 0.6 times the minimum of what? So let's do each of these separately. So what's the top one? 220 kips, and the lower one. So we'll just say 206.4. Right? Okay, so we take 27.6 plus 0.6 times the minimum of these two. So 27.6, sorry, look, kips plus 0.6 times 206.4 kips, and that equals what? 151.4. Do I have a second on that? All right. Now, what happened to this? I must have erased it accidentally. Oh well. Okay. Now remember, that's the block shear capacity of a single block, right? That's a single block. Is that the block shear capacity of the whole section? No. So next thing we have to do is we have to compute the block shear capacity of the whole thing, okay? And so what do we multiply that by? Because there's 4 blocks. So 4 times that. And so what does that come out to be? 151.4 times 4. 605.8. Now, is that done? Why? We have a phi value, right? We have a resistance factor. This is a nominal capacity. We don't care about nominal capacities in LRFD. We care about design capacities. So we need to adjust that by our phi value. And so what is phi? 0.75 for block shear. And so what does that come out to be? 454.4. Do I have a second on that? I do? All right. All right. Let me ask you a question. Does this govern? Does block shear govern this section? No, it doesn't. Because, so what ultimately governs the capacity of this section? The net section fracture. If I yank on this thing, what's the first thing that's going to happen? It's going to fracture along the net section before it yields in the gross section and before block shear happens. Now, you didn't know that block shear didn't govern until you went and did the math, right? Sometimes it will, sometimes it won't. Okay? Are there any questions on this? Yes?
Is there like something that'll tell you, like, if you look at the whole layout?
That's a good question. So the question was, is there a way that you can look at the connection and see whether or not block shear is going to govern? The short answer is no, but there are some hints where you can see whether or not it's going to be a big deal. For instance, if you got really big bolts that are really close together, that means that your net areas are going to be really small. So if your net areas are really small, then that's kind of a big deal. That would be sort of the easiest way to tell. Now, that doesn't mean you can't not do the math. Like, you still have to check it. So, but that's the giveaway. Yes. That's a great question. So the question was, do you account for this during design? No, but you need to check it afterwards. Typically what you'll do, and this is true with tension member design as well. In fact, there's a problem on your next homework assignment that's like this. I'm giving you a problem and I'm saying design and account for block shear, and really all that means is just check block shear at the end. So what you'll do is, if you were designing a tension member, you would design the tension member according to exactly what we did, and then just check block shear at the end. Now, if block shear governed and it didn't work, you've got a couple of options. And let's talk about those options. You could pick another member, right? You could pick another channel. You could space your bolts out further. Because think about, that's actually probably the most benefit, or the most beneficial way of improving your block shear capacity is to space your bolts out a little further. Because increasing your bolt spacing is going to substantially increase your block shear capacity. Changing your bolt pattern, which, answer that right now because I know somebody's probably thinking about it. Am I going to make you do a block shear problem on a staggered bolt path? No. The answer, how you would do it, when you do your gross area and your net area and tension, just add a stagger factor. That's it. But no, I'm not going to make you do it. So, you know, don't worry. I won't do that to you. Yes?
When we're looking at our tensile pads, how many bolts it takes out?
Yes?
The way our line looks, it kind of looks like it only takes out half a bolt every time. Are we assuming it just takes,
What?
like, when we multiply the shear path by 3.5, like the line kind of cuts the bolt in the middle?
Well, yeah, because so you've got, let me do this. So you have 1, 2, 3, and then a half. So, what? 1, 2. What happened? My surface is haunted. So 1, 2, 3, and a half. But
Okay, when I was looking at it, I was thinking it was like half a bolt each time, and the tensile bolt up there would be a fourth.
no, because a whole bolt hole would be going through the whole thing, but it's stopping in the middle. So you could think of like 3 diameters and a radius, but a radius is just half a diameter. So the more you know.
Thank you for clearing that up.
It increases your net area. So it helps from a tension member capacity, and yeah, it can help from a block shear capacity, but that's not really the real reason that you do it. The real reason that you do it is to increase the net area. And here's another thing. You can increase the net area, but you can also usually kind of keep your bolt pattern concentrated, and that's good from an economic standpoint. In other words, if I could keep my bolts like this, as opposed to spacing my bolts out like that, that means that I don't need as big of a plate to connect that member to the adjacent point in the structure. So more often than not, when you're designing connections, you like to keep your bolts like this and not space them out. Because the more you space them out, that means the more steel you need to connect it to the next member or to the gusset plate or whatever. So, what's so funny? We're not talking about eye bolts yet. We'll do that later. You opened it up. All right. Chill out, guys. All right. Any other questions? All right. Now, before we close it out today, I got another topic I want to talk about, and unfortunately, it's a little serious. It's kind of a big deal. How many of you have heard of this? A couple of you. Anybody heard of this? No. This is in Kansas City. Yes. All right. This is kind of serious. All right. This was a structural failure that happened in the early 80s. This took place in a hotel. It was the Hyatt Regency Hotel. And to give you kind of an idea of the severity of this event, this is the worst failure of a structure under its design load in the history of the United States. There were over 100 people that died this day, and close to double that were injured. Okay? Now, I'm sure some of you are thinking, like, well, what about 9/11? What about the Oklahoma City bombing? Like, wasn't that worse? Yeah, that was worse. But it was not under its day-to-day normal operation design load. To give you kind of an idea, how many of you have heard of I'm sure you all have heard of the Oklahoma City bombing, happened in the mid-90s, right? Okay, all right. So to give you an idea of what happened to the structure, so when the Ryder van was parked next to the building and it was full of explosives and the bomb went off, to give you an idea of the severity of that explosion, the truck was parked right next to a main support column for the building. That column supported something like 30 stories worth of load. That column under that blast load experienced what's called a brisance failure, which basically means it shattered. Okay? We're talking about a steel column that supported 30 stories of a building and it shattered. They reported broken glass in windows from up to a mile away from that blast. That is not day-to-day operation of the building in any way, shape, or form. This was. Oh, God. I'm ignoring that.
Did he do that on purpose, or was that just luck?
I'm going to answer that question. I think I'm going to be honest, I think it was probably luck, because I think he probably parked the truck and ran, and so I think it was luck. But let's be honest, if you pack a van with that much explosives and park it next to a building, it's going to be bad. So I think he was aware of that too.
I'm sure he was.
Do we need to have another ethics discussion? Goodness gracious. My goodness. Look, what happened at the Hyatt Regency was unique in the instance that in this event, the element that failed was experiencing its design load. This was what it was designed for, and it still failed. And so this was a really, really significant event in the history of structural engineering. What had happened was this. This was in the lobby of the hotel. I don't know if you've been in a lobby of a major hotel, they tend to, you can host big events. And so this was in the early 80s, and so they had these sort of like tea party type events, and so they'd have, hundreds of people in the hotel at a given time. And so this is what was going on before the collapse. And so, so the ground floor, they had like a band, and there was sort of like a jazz band, and there was all these people. There was like a bar, a dance area. Everybody was sort of having, a good time. And there was a second floor skywalk, and there was a fourth floor skywalk. And see, here's the connection, okay? This is the connection, and the connection involved the inclusion of a threaded rod. Well, what happened was this connection right here between this second and fourth story, it essentially ripped through and collapsed, okay? So not only did the second floor skywalk fall, but the fourth story skywalk fell on top of them. I don't know what that is. But yeah, to give you kind of an idea, so this was before and this was after, and so the walkways not only fell, but the upper walkway fell on top of them. So a lot of people really didn't have much of a chance. Now, that's what happened. Here's the why. If you look here, this is the detail of that skywalk connection, and this is an as-built detail. So this is actually how they built it. This is how the structural engineer designed it. See, the structural engineer designed this skywalk system to be supported by a series of threaded rods that ran continuously from the ceiling to support both skywalks. But the contractor didn't like that, because the contractor didn't want to have to thread that fourth floor skywalk all the way up. So the contractor decided it would be a good idea to separate that into two separate threaded rods and just drill another hole and bolt accordingly. I mean, it saved him like $25 a connection. That's an interesting point, though, what you're saying. Nobody was, I mean, that was just decided. Structural engineer was never contacted. But hey, he saved $20, $25.
How many holes did you drill?
What's that? Oh, it's the contractor's fault, but let's just say just about everybody that touched this project, their license was in danger. Let's just say that. You're right. I mean, everybody that affected, that touched this project was in jeopardy, and just the sheer amount of dollar figures, the sheer amount of dollars that were let out from settlements of lawsuits. I mean, it was ridiculous. So what happened was, by separating this into two separate threaded rods, what happened was they doubled the shear on this connection, and it ripped right through, and boop, you had over 100 people dead, and almost double that injured or wounded. Yes. I'm actually not 100%, but I know that on this night, like this, when this party was going on, like these events at the Hyatt Regency were starting to get a little more popular, so more and more people were coming, and so this one night was just too much. I don't think the hotel had been around for decades. I think it was a fairly new structure. I don't remember specifically when. So. Well, it changed the distribution of shear along this box beam. The box beam was designed to see just that single load, but instead it's seeing a shear distribution that it didn't expect. And so, to be fair, it wasn't really the threaded rod that failed. What failed was the box beam that threaded rod was connected to. So yeah, this is kind of serious stuff, folks. I mean, I don't want to, I know I'm an easygoing guy, but I mean, I just want you to sort of recognize that this stuff is kind of important, So, when I say things like write that KSI, write the KSI. Write it out, because this is the type of stuff that happens. So just be cognizant. What I want to do is use that as sort of an extension of how do you properly design threaded rods. Threaded rods are one of the simplest forms of a tension member, because of the inherent nature of threaded rods, you only have to consider one limit state, and that's net section fracture. You don't have to consider slenderness because threaded rods are inherently slender, so they're meant to operate in that fashion. So you really only have to consider one limit state, and they're easy to design. Now, in terms of available bar diameters, if you solve for a threaded rod bar diameter and you get 0.72368, you're not going to use a 0.72368 diameter rod. You're going to use the next commonly available diameter. So typically, threaded rods are available from 1/4 inch to 1 1/4 inch in 1/8 of an inch increments. So 1/4 inch, 3/8, a half, all the way to 1 1/4. And then anything past that, it's going to be in 1/4 inch increments up to 4 inches. So threaded rods can be pretty beefy. They're meant for diagonal bracing. They're meant for sag rods to prevent excessive deflection and other elements as follows. Now, how do you determine the capacity of a threaded rod? It's pretty straightforward. You just need a nominal tensile stress times the area. So in this instance, what's the area of a rod? Well, it is pi over 4, d squared, because we're talking about the area of a circular cross-section. The phi value is 0.75. The only thing you need is a tensile stress, like a nominal tensile stress of the rod. This actually comes from the chapter on bolts, which we are going to have some significant experience with in the very near future. If you go to chapter J and you look up the nominal tensile capacity of a threaded rod, it's always going to be 0.75 times the tensile stress. The way that this table is structured, it lists different stresses, whether or not the threads are included or excluded from the shear planes. That doesn't matter for a threaded rod because we're not shearing it. We're applying tension to it, so we don't have to worry about that. That is going to become a big deal here in a little bit when we talk about bolted connections. So regardless of either of your shear plane, your nominal capacity of a threaded rod is 0.75 times FU. So here's your nominal capacity. This is 0.75 FU, and you have another 0.75 from phi, so the phi RN is pretty easy to compute. And since there's only one limit state, you don't have to consider slenderness because threaded rods are inherently slender. It's not appropriate for that type of element. It's pretty easy to actually solve for the diameter. See, 0.75 FU AB, what is AB? Well, it's pi over 4 dB squared. 0.75 is 3/4, so you can do a little bit of algebra and solve for what's the minimum bar diameter, and it's a plug and chug expression. It's pretty straightforward. It's pretty simple. So this is just me taking the math, solving for dB, and simplifying the fractions, and that's what you get. So it's a pretty straightforward computation. And so on Monday, what we're going to do is we're going to do this problem. And so you can probably kind of guess how I developed the example problem, because we're going to be designing A36 threaded rods for a suspended walkway. That's not funny.
I hope we do a better job.
Well, I do too. Now, all right. I guess, yeah, that's really all I have for this time. What we're going to do, just before everybody leaves, what we're going to do next time is we're going to do this example on threaded rods, and then we're going to start bolted connections. I want everybody to pay attention to what I'm about to say. After example 7, that's exam 1. Bolted connections, that's exam 2. Exam 2 is on bolts and welds. So that's all I have got for you, everybody. You all have a wonderful weekend.